Alright, here we're just gonna do a derivation of a volume for a cone. Something like this, and like this. That's a cone. So we're gonna derive the volume for a cone. And remember, here we're just gonna have radius r and the perpendicular height there, height h. The perpendicular height there is just gonna be our height h and r there. So, how do we derive the volume for a cone? So, as always, we'll need the axis there. We need to represent this on a Cartesian plane. For simplicity reasons, let's say we start from the origin. You can start from anywhere you like, but then for me, I just think it's simple to start from the origin. And then from there, we have a line. It's a line with some certain gradient there. And then we have a height there. A line y equals h. This will be a line y equals h. So that means that here we will have height h there. And then here, let's say we have a coordinate r h, right? RH. This we have a coordinate RH because here we're just gonna have a radius r, and as if we've already guessed, we'll be rotating about the vertical axis. And then from here, let's find the gradient. M equals y2 minus y1 over x2 minus x1, and y2 it's h and x2 it's r. Y1 is 0, and then x1 is 0. So you just have a gradient h over r, and your equation of that line, since it passes through the origin, will just be mx, or just it's gonna be h over rx. So if we have like a straight line defined by h over rx, or y equals h over rx, and then we're rotating about the vertical axis, that means we need to solve for x. Remember, the formula is given by something like this: volume equals pi, the integral from a certain region r at y, square dy, if we are rotating about the vertical axis. If we're rotating about the horizontal axis, it will be x dx, right? R at x dx. And then from here, that means we have to solve for x, and if we solve for x, that means we multiply by r over h on both sides. Then we just have r over h y. That will be x. That will be our r at y. And we're going from 0 to h. We're going from 0 to h. So the volume of that cone, we're moving from 0 to h, and r at y will just be r over h y, square that dy, and then v, and then you have r square over h square y square. We have from 0 to h, then we have r square over h square y square dy. But notice that r square over h square is a constant, so you can take it outside the integral. Then we have pi r square over h square, and then we have the integral from 0 to h y square dy, and then from then the integral of y square dy, pi r square over h square. The integral of y squared dy will be y cubed over 3. Integrate that from 0 to h. And then from then we're just going to have h cubed over 3 minus 0, which is just going to be h cubed over 3. So we have the volume of that being pi r square over h square multiplied by h cubed over 3. And remember, h cubed, we can rewrite h cubed as h square h multiplied by divided by 3. Then this h square and h square will cancel out, and then you have the volume being pi r square h over 3. But you often see it written as something like this. Our volume will be equals to 1/3 pi r square h. That will be a volume of a cone. So that's the derivation of a volume for a cone. Basically, you can play around with these things. You can like have a parabola instead. You can have a parabola instead, and find the volume obtained by rotating rotating the area bounded by the graph and the y-axis, and then you find the volume of that by rotating the area bounded by the graph and the y-axis. And you can do that for like any function you have, just to check if you understand these things. Thanks for watching. Don't forget to share and subscribe. And as you can see, these things are technically simple, really. But then we're gonna start doing other methods. Remember, this is the disk method, so we're gonna start doing other methods for solving these things. Don't forget to click the notification bell to get notified whenever I make an upload.